proceed, Gaetano. Hi.
Thank you, thank you. Thank you, Davide. Good afternoon to everyone. It's a pleasure to chair the session 3 of this amazing symposium. The title of the session 3 is Smart Innovations for Transport Networks. I will introduce 3 SMARTI fellows, Ronald Anthony Roberts, Iain Dunn, and Philippe, I apologize for my bad pronunciation, Philippe Sohouenou. I think there is a very interesting session because by comparing this section with the previous 2, I think we will face different issues and topics, and this is an opportunity to integrate the information and visions of the SMARTI project in the and its complexity in its overall view of the research. So I give the floor to Ronald Anthony Roberts. He did his research activity at the University of Palermo under the supervision of Professor Laura and me. Please, Ronald, you have the floor.
Hi, good afternoon, Prof. Good afternoon, everyone. Can you hear me? Hello?
Yes, we can.
Okay, great. Okay, so can you see the screen?
Yeah.
Okay, great. Good afternoon, everyone. I guess for the last time, I introduced myself. I'm ESR number 12, Ronald Anthony Roberts. My project was entitled Sustainable Road Management Through Low-Cost Techniques, SuRoMa, if you will. And as Prof said, I was supervised at the University of Palermo by Professors in Rio and, of course, Professor Di Mino. Just to give you a background of why this project was important and what was the motivation for it, it was basically to help road managers. Essentially, road managers all around the world have a lot of questions to ask. They want to know which roads do they fix, when do they fix these roads, how do they fix these roads. They have a lot of questions, but they don't have a lot of solutions. The project was built basically to answer these questions, providing them with cheap, but at the same time, accurate and sustainable techniques and systems, so that they'd be able to answer these questions and have better pavement management systems in place to proper manage your roads and have better conditions throughout their networks. With that in mind, the project had basically 3 main concepts, which the first being using data analysis to look at limited data sets to understand historical and future road maintenance interventions. The second being to consider that the subjectivity that is involved with detecting pavement distresses and to try to find new novel methods using image-based 3D modeling. And then the final aspect was dealing with deep learning to try to detect and pinpoint pavement distresses within a network. I'll go straight to the first concept. So basically what we did was try to take data that was readily available, open source data all across the municipality in Palermo, which included census data, traffic and commuting data, economic activity data, and of course, historical maintenance data. But the idea being we could utilize the stuff that is already available without carrying out a tremendous data collection campaign. And once we had that data, we collated it across the different factors across the municipality, building a database of about 20, a little bit above 20 different factors. Then we carried out a series of data analysis and feature selections, particularly using open boost systems such as Cat Boost to try to identify which of those features were actually important to predicting when the next pavement intervention should take place. So with that, we came up with these are the most important features, at least for this data set. And methodology, of course, is something that could be applied to other municipalities. Once we had these important features, the next step was building a framework using deep learning to see if we could model and predict where those interventions would take place in the future. With that in mind, we came up with, using the fast AI deep learning network, we came up with a series of predictions which had an accuracy of about 87%, which is pretty decent. I won't go into all the nitty-gritty aspects of it, but you can find a lot of information on the paper that you see at the bottom there. The second, I'll go straight to the second concept, which is basically dealing with 3D modeling and image-based detection systems. But before we got into that 3D modeling, we had to understand exactly how our pavement distress is measured. So we took the different manuals from across the globe, from all the way from Australia to the US to Europe to all the different continents, to understand exactly how pavement distresses are detected and how they're measured. And with that, we came up with a methodology of what was important in each group and what is the characteristics that you require for a new technique. So before we can launch the image-based systems, we have to understand what exactly it is. And more data can be found in that paper you'll see at the bottom there. So with that, we went straight towards structure for motion modeling, dealing with 3D models, basically, which takes 2D images and that are collected in an overlapping manner. And using that, you could predict a 3D model of the actual distress and the actual, basically, of anything really. So what you see there is just an image of the pavement at the top, and then at the bottom is the 3D model that was created basically just from those 2D images. With that in mind, you could then take the 3D model and you could have cross sections along it. You could pick up a lot of really important information, such as the depth, the volume, the area, and you could have this along the entire section, basically creating a huge asset towards the pavement manager that will be very useful. And again, some of the information there, more details can be found in that paper. The next step was basically segmenting those 3D models so you could isolate the distresses within the different sections. So you could easily pinpoint which sections have the distress, the area that is affected by the distress, and the level, the depths. It's so much information that you can take from a 3D model versus just those 2D models that you have. Again, more data is there in that paper that you see there. And then finally, we also wanted to consider drones, because with a drone, you can actually do a survey over a larger section versus the pinpoint cameras. And we did a survey over a very large section to see how this would actually work. And we were able to achieve a really good accuracy that could get, you see there, the ground sample distance of about 0.97 millimeters, which means that you could have an accuracy to about 3 millimeters for the distress, which is perfect based on the data that we found within those manuals. And with that, we came up with sort of a methodology where you could use that information and sort of have an analysis of the average level of distress over the various sections. So you see that same section there. Now we can model it, and basically you have all of the areas that have distress over it. You have the average level of distress for the entire section. You also have which subsections have more distress. So basically, if you did the survey in a large landscape, you could then, after carrying out the analysis, you could have a fairly good understanding of what exactly is happening within your network, and you could replicate it and keep storing that data over time to sort of produce more data for your asset management. And then finally, the last concept that I'll talk about dealt with the deep learning. We did this in two contexts, the first being using Italian in Italy. Actually, Gaspare helped me out a lot with this. We had a camera that was embedded in a smartphone, and he drove around Sicily a lot, basically collecting images, building a giant database, which I then labeled based on the types of distresses that are available, and using that, created a deep learning model that was able to detect where the distresses are within a network. At the top there, you'll see some of the examples of this using some real-time images, and the accuracies we got out as well were pretty good, identifying that a process could work, especially for this scenario. And again, it gives you this information possibilities in real time. It also gives you can do it afterwards, after the survey has been done. So there's a lot of opportunities here. We work this out to sort of a framework that you see here, but again, more information can be found in that paper if you want to find out more about that. Then the next step was to consider it in a different context. And for this, I considered my images that I procured during my secondment in France. And basically these images were different because they were from a top-down perspective. And we also considered different types of distresses for this. But the idea was to sort of use the same methodology to see if we could make it work. And we were also very successful in doing this. I'll just show you a few of them in a video showing some of them in real time here. You see that some of them are being missed, but at the same time, it gives you an idea of what is possible with this sort of technology and what is possible with these sort of results. So we were pretty satisfied with this, and we did a lot of also optimization and augmentation that are not shown here, but you can find a lot more information on that in the thesis and in papers that I've done. So to conclude, basically, I like to think of it as considering the two different aspects with two different questions. If you have a need, basically, as a road manager to have pavement distress data, understand the maintenance timeline, then you can look at the data and analytics part that I spoke about, and also the deep learning with the phones. But if you want the detailed metric analysis, that's where the photogrammetry comes in and the structure for motion and the 3D modeling. But the idea is that you need both of them sort of to give you the answers to provide towards your pavement management system so that those road managers can actually help their networks and have less questions to answer. With that being in mind, I'd like to thank you for your attention, and I'm happy to be here. And if there's any questions at the end, I'd be happy to answer them. Thank you.
Thank you, Ronald. Thank you because you were in time. Thank you. So I give the floor to Dr. Dunn. He did his work at University of Palermo under the supervision of Professoressa Antonia Pirotta. Please, Iain, you're welcome. Please, you can start.
So just to make sure everyone can see my presentation, right?
Okay. Yes.
So thank you for the introduction. As Gaetano said, I studied with Professor Pirotta, and my project was number 6, which was titled the SMART Damper. So bearing in mind the time, I'm just going to dive straight in, and I'm going to apologize for the fact that the first slide here is entirely text, but just to give a little bit of background to the project. Although it's titled Smart Damper, it's actually about a novel formulation to introduce a smart damper to a rail or a road bridge. So what we were really looking at was novel analytical mathematical methods to analyze the dynamic response of an Euler-Bernoulli beam, which is a common mathematical model of a bridge, or a mathematical representation of a bridge, to loading. Typically, there are 2 ways to conduct this type of analysis. You have the classical analytical method, and you have finite element analysis. Both of these have their advantages and their disadvantages. The advantage of the classical method is that it is extremely accurate. However, it is very computationally inefficient. Whereas with finite element analysis, it is extremely computationally efficient. However, it introduces a degree of inaccuracy, particularly if we're talking in the case of modal analysis at the higher modes of vibration, at higher frequencies. So the goal of the project was to create a novel analytical method that had the advantages of both with none of the disadvantages, i.e. a highly accurate and highly computationally efficient model. And the goal behind this was to be able to perform what we call virtual experiments. Essentially, this is when we have a mathematical or a computational model that is so accurate that it allows us to test new designs, new materials, new types of attachments. Rather than doing in situ testing or small scale testing, we can use the computer model and be very confident in our results. And this also ties into sustainability. If we talk about new structures under design using more environmentally friendly materials, or even slender structures to save on the amount of materials, we want to be confident that these will perform as well as traditional structures. So This, I'm not going to go into too deeply. It is the classical solution method. And the only takeaway that I want you to have is that if we look at this beam here, which is a relatively simple model of a bridge, it's 4 spans long, it has 3 tune mass dampers. In this case, we would need 4 individual equations of motion, which are of course coupled. And then we would have 16 unknown constants from these equations of motion. All of these must be solved simultaneously. And as you can imagine, this takes a very large amount of computational power to do. And this is a simple case. In real world applications, you're looking at beams with far larger spans. So in this simple case, you're still talking minimum 1 day to conduct the analysis. And that's when the model was already prepared. This is just the time for the computer to do to conduct the analysis. So the proposed method, the novel method that we developed over the course of this, allows us to consider each of these attachments or discontinuities. Instead of that starting a new span, it is modeled instead as a reactionary force, a point load acting on a specific intraspan point. And this means that essentially we go from 4 equations of motion to analyze this simple model to 1 equation of motion. That, of course, is performed through this term here, which is our R of x and t. That is the term that accounts for the reactionary forces, and it's expanded here. Of course, it will be different depending on what our attachments are at these points. So a further expansion was then proposed, which we called the helical spring model. Typically in a tuned mass damper, we do not consider the mass of the spring. The spring and the damping element, in fact, are considered to be massless. All of the mass is contained in the lumped mass. However, obviously, this is not how things work in the real world. So with a view to creating these virtual experiments, what we wanted to do is have a far more accurate model. And to be more accurate, you have to remove assumptions. This was our opinion. So we developed this equation here, which is the model of the entire tuned mass damper considering the mass spring here. And as you can imagine, or as you can see, in fact, this is far more complex than our typical model for a tuned mass damper. However, applying the limit case where rho spring J, which is the spring's mass, in fact, its distributed mass, tends to 0, you see that it returns to the standard equation. So we can be pretty confident that it is a good representation. It is far more accurate, or I say far more accurate, compared to removing assumptions. And you can see this in a numerical example. So this is just for the sake of knowing exactly what parameters we have, but these are the numerical results. So validating with finite element analysis, you can see that we have a very good agreement between the results from the helical spring model and the lumped mass model. And then looking at the graph, you see that the response is very, very similar, but that the helical spring model does seem to outperform slightly the spring mass model in terms of maximum deflection, which may be expected as we have a higher mass that they've been considered. This is just to say that the model does have some advantages over the classical way of modeling a spring. However, it's debatable whether or not that is worth it for the extra complexity. The next stage that we moved on to was Poissonian loading. Poissonian loading, as it says here, is a special case of random loading in which the loads arrive with random magnitudes at random times. The reason we did this type of analysis was because it's similar to traffic loading that we would see on a bridge. You know, typically vehicles traversing a bridge will arrive at completely random times with completely random magnitudes. However, they will be moving at roughly the same speed and in the same directions. So Poissonian loading can be quite a good method of representing. The application to the beam is shown here, where instead of F of t, we have our Poissonian load here as a forcing action. As I mentioned, we have the independent variable, which is the amplitude of the forcing actions. We have another random independent variable, which is the arrival times. And then we have a counting function, Dirac's delta, to localize where the force will be at a specific point in time based on the velocity, and a window function to remove the load once it's traversed the bridge. But I'm not going to go too much into detail to that either. So we then moved on to conducting some experimental analysis in the laboratory here at the University of Palermo. And the purpose of this experimental analysis was more for our own confidence that our analytical methods were working. So this here shows the setup, and you can see that we also have an attachment at the midspan here. Here we see the locations of the contact accelerometers used to obtain the results from the experimental analysis, and the results are shown here. And you can see that there is very, very good agreement between the two, the discrepancy never going higher than 1.75%, so always under 2%, at least considering the first 5 modes. This is, of course, what we would like to see. And here we see that the analytical method using the classical representation of a tune mass damper is slightly less accurate at times, but also perhaps slightly more accurate, in fact, than the version that uses a more accurate helical spring model. But it's our belief that this is most likely due to inaccuracies in the design of the small scale experimental model, because we did have to do a rather large amount of system identification once it was built, due to the materials not matching properties that they should have. So to conclude, and again, I'm sorry for the wall of text, we first developed a novel method. This formulation has significant advantages over the classical formulation, particularly when it comes to the equations of motion. The extension to the Mach model in the terms of the helical spring model was presented. We then subjected it to Brownian loading to introduce a stochastic element. And finally, we had results from an experimental campaign. So thank you for your attention. I'm sorry for rushing through this so quickly, but if you have any questions, I'll definitely be here.
Thank you, Ian. So for the question, we will do that in the session in question time after all presentation are made. Okay.
Yeah, I'll be here. Don't worry. Thank you.
Yes. So I have a question just for you. Just for you. Now I give the floor to Philippe. Philippe is here. I hope so.
Hi. Hello, everyone.
Philippe.
Yes, I'm
welcome.
Here. Thank you, Prof.
You can start. And so I guess you did your activity research under the supervision of Professor Luis Neves at the University of Nottingham.
Yep, exactly.
Correct?
Yes,
correct.
That's correct.
Philippe, please.
Okay, so let's start. So, hello everyone. Nice to meet the people I don't know. So right now, I'm a project manager and transport resilience lead at Resilience, which is a consultancy that provides analysis, innovative solutions, and project coordination services for climate adaptations of infrastructures, cities, and territories. And before joining Resilience, I was in SMARTI from 2017 to 2021, where I was a researcher at the University of Nottingham, like we just said, and I focused on resilience engineering. And I also did part of my SMARTI project at the EU Joint Research Center in Seville, in Spain, to work on transport analysis. The name of my project was ResilRoad, for resilience indicators for road networks. So a bit of background around the project. As you all know, roads are very critical assets that support the mobility of people and goods. However, they are often disrupted by failure of aging infrastructures like bridges, terrorist and sabotage actions, and also extreme weather events like flooding. And this has a huge impact on people and the economy. So for example, the 2007 UK flood in the UK led to 10,000 people being stranded in London and repair cost of 40 to 60 million pounds. So based on this, society needs resilient road networks. What I mean by resilient is able to sustain and quickly recover from disruptive events. However, current transport planning, modeling, and management standards provide little guidance on resilience. So the aim of my project was to develop guidelines and modeling tools to support decision makers into predicting, assessing, and ultimately reducing the impact of disruptive events on a given road network's performance. So I will quickly go through the project methodology, then I will provide some studies and results, and I will finish with some conclusions. So first, the methodology. So the idea was to develop more accurate and meaningful method for quantifying road network resilience, in particular considering multiple possible disruption scenarios, and then apply these methods to case studies, including artificial and real networks to test and validate the methods, and then also use the case studies to explore the effect of network characteristics, like the size, the topology, the demand distribution on the network resilience, and the effect of repair strategies on network resilience. So first of all, if you look at the literature, there's a lack of consensus and rigor of the use of the term resilience because it is used in different disciplines like economics, ecology, engineering, psychology, that are all adapting it to their needs. And then it also overlaps with other concepts such like risk, robustness, and reliability. So the first thing I did during my PhD was to look at this and to summarize. Basically, system resilience in engineering can be linked to three concepts. First, it is to reduce consequences, then reduce recovery time, and finally reduce future vulnerabilities. And there's a difference between risk and resilience, meaning that risks focuses on predicting and reducing failure. So you think about the probability of an event happening, and resilience accepts the possibility that certain failures are unpredictable. Basically, you cannot have the probability of occurrence of the failure, but you still focus on reducing the impact. So you prepare more or less for everything. So based on that, I propose to assess resilience as the capacity to absorb perturbation, which is robustness, and the capacity to recover quickly, which is rapidity. And then for the system, the idea is to focus on its ability to deliver its functionality, usability, and not its integrity. So if you consider a road network, if you lose, for example, one component or one road, but you are still able to go from point A to point B more or less in the same time, the network is considered resilient. So now we look at resilience quantification. So basically, this graph shows how the indicators that are developed and how we can measure resilience. So what you can see is that there is network performance that is normal at the beginning, then there is a disruption happening. So the network performance decreases until a certain level of services, and this provides a network robustness indicator. And then you will look at how quick the network is able to recover its functionality, and this provides a rapidity indicator, and both the combination of both provides network resilience. So basically, this graph shows how to quantify resilience. It's the same thing that I showed to you before. We have disruptions, and we look at network performance, and we can, after, compute different indicators about the idea of my model is to use another independent model. So basically, we don't look at the causes of the event, but at the consequences. And to repeat the process for several damage scenarios, and then look at statistical analysis to compute what will happen in a lot of different scenarios and understand the resilience of the network to multiple scenarios. And the idea of the network performance indicator is to compare the normal and the disrupted travel time on the different origin-destination pairs in one network. It uses a weighted average computed across all OD pairs, which basically gives more importance to the highly demanded OD pairs. it's scaled between 0 and 1% for clarity. And basically, compared to indicators that are often used in the literature that are based on total travel time losses, it's able to discriminate between a lot more scenarios. This is shown in this simple example here, where basically I computed the disruptions of different links. This includes single link failures and two link failures. I will not go through the details, but if you look at the columns completely on the right, you have the proposed robustness indicator and the total travel time losses. And when you look at the bottom, you can see that the total travel time losses is the same for a lot of different scenarios on the far right. But if you look at the network robustness, you see that there are different values, meaning that you can discriminate between a lot more scenarios than with the total travel time losses indicator. Then I performed a lot of sensitivity analysis to understand how resilience is basically influenced by different characteristics of the network or of the way the network is managed. So the idea was to perform resilience analysis on a variety of road networks. This included artificial networks that are generated through a model that I developed that you can see on the left and in the bottom, and also real networks that I extracted from real maps using OpenStreetMaps that you can see on the right in the bottom, and looked at different attributes, so network size, the number of intersections in the network density, the link cost heterogeneity, which is, for example, the standard deviation of the link travel cost. When I talk about travel cost, I'll talk about the travel time on the different links of the network, for example. And this allowed me to find, for example, relationships between network attributes and resilience. So here you can see how the resilience evolved for different networks depending on the number of intersections that are in the network. And this shows, for example, that redundant routes, which is the additional roads and intermediate intersections that you can build into a network, can enhance the resilience, but it is only up to a certain size and connectivity thresholds. And this is interesting for network design, as there's a conflict between network resilience when you want to increase the number of roads and intersections, compared to network efficiency, where you want as little redundancy, and you want as few roads as you want to increase efficiency. Then it also showed that, for example, that the identification and protection of the most critical road segments is crucial in networks that are really dense with a lot of intersections and roads. Whereas in sparse networks, most of the links are equally important. And this has impact, for example, for network management, to know that in certain networks, you need to prioritize certain roads, and in other networks, you really need to protect all of the roads. Another findings is basically I looked at how repair strategies can influence network performance and the unsatisfied demand in a network. So this is the graph that you can see here, where I looked at different strategies and the impact of the repair strategies on the network performance. And this allowed me, for example, to show that for a network that is not congested, the priority is to reconnect stranded travelers to the network. Whereas in a network that is highly congested, the priority is to reduce congestion before allowing people that are stranded, so blocked in some place, to enter the network if you want to increase the overall performance of the network. So to conclude, I gave you an overview of my project ResilRoad, which deals with a burning issue for society, which is the resilience of transport networks. I developed a conceptual framework explaining how to assess road network resilience and some indicators that provide an accurate and meaningful tool to quantify resilience. And the sensitivity analysis that I performed led to multiple insights and findings with implications for network design and management. And to repeat, the long-term objective of this project was to help incorporate resilience into transport planning, modeling, and management standards. So I published different publications that are available on ResearchGate or on my blog that I had and I did with SMARTI. And with that, thank you for your attention. And I remain here to answer any questions.
Thank you, Philippe. So, Davide, do you agree to start the session, the question time right now?
Absolutely, yes.
Absolutely. So, any question for Philippe, for Iain, and for Ronald? Simone has a question.
Yes, Simone.
Yes.
Please, Simone.
Thank you, Gaetano. I have a question for Philippe. I would like to know if with the model you develop, you are able to evaluate the impact of dynamic signaling systems. I mean, for example, dynamic lightning systems on the resiliency of, or the resilience of a pavement. I mean, if you are able to anticipate any I don't know, traffic disruption in the road with monitoring, for example, or with I don't know which kind of device. Then if you are able to anticipate that, if there is if you can, I don't know, evaluate the impact of dynamic signaling systems with your model, or not.
I think that's something that I didn't consider.
Okay.
Basically, it's a bit more advanced. And I focus simply on looking at the road network and putting some disruptions directly on the roads. Of course, this can come, for example, an issue with the pavement, but this is like a new add-on to the model per se.
Okay. I think it could be something interesting to study, but now you are in other projects maybe.
Yes, but but maybe sometime we'll be able to go back to that.
Thank you for your presentation. It was interesting.
Philippe, I have a question to you. So I didn't understand if your research is based on real data or a simulation data.
It's mostly based on simulation.
Okay.
The only thing is I have data from real networks where basically I know this is a real network, how it works, but I didn't have data of a disrupted real network. So I couldn't compare with a disrupted real network. So I used the real network and I simulated disruptions onto the real network, but I don't know how in reality the disruptions will have impacted the real network.
Thank you. Thank you. So last question. My last question is for Iain. Iain, looking at your Iain.
Yeah.
Okay. So looking at your slide on the helical spring model, it seems that the question becomes more complex. Probably you gain in accuracy, but the complexity of the model, it worked. Can you show the slide, please?
Sure. 2 seconds. This slide, and I'll just share the screen.
Gaetano?
Yeah.
Just to say that there is also Henry that wanted to ask a question after.
Okay, so this is, no, not this. This is the slide you're talking about.
Yeah, right? Yeah. The helical spring model, yes.
Yeah.
So, because I see a K with a more complex formula.
Yes, it's far more complex. But I guess the complexity is is in developing this rather than the analysis. So at the stage in which this is analyzed, you're considering the free vibration problem. So you would have an equation for how the beam would react in free vibration, and then that equation is constant no matter which type of loading you apply. So although this is far more complex, and it is, and I think it's worthy of debate whether or not this added complexity is worth it in terms of the advantage you get or the increase in accuracy you get. But once it's developed, there is little more complexity added in its implementation. So now that it has been developed, I see there being no reason not to use it, I suppose. If that answers the question.
Thank you. I see I raised the hand. Please. Please, the question.
Henry. Thanks for
Henry, we can't hear you properly.
No?
Nope.
I think maybe the mic isn't folded down. The mic seems to be.
Yeah. Looks like the mic is in the other room.
Can you hear me? I've got a headset on.
We can hear you faintly, but I think your mic isn't folded down on the headset as well.
So, okay.
I've checked. Can you hear me now?
Better.
Better. Us.
Oh,
No?
Henry, please, the question.
Okay. Thanks for the presentations, Ronald, Philippe, and Iain. I've got two questions, one for Ronald and the other for Philippe. Ronald, as you know, just as maybe as a little background, I am more in developing countries. I'm more in my line of work. I work closely with developing countries. So I just wanted to understand, Ronald, for your dashcam, are there any standard specifications? Because I find what you've done relevant to road authorities in developing countries. You know, that sort of intermediate level means of collecting data for road networks. But are there any specifications you can give for what that dash mounted cam should be in terms of collecting the data on the condition and various defects you pick up? That's for you, Ronald. The other one for Philippe is the framework you've developed to measure resilience. Is it, what's your take in terms of applicability in developing countries on networks? We're talking about low standard, maybe low volume roads, maybe engineered gravel roads, or sometimes just mud roads. What is your take in terms of applying the framework you've developed to measure resilience on such networks? Thanks.
Okay. Hi, Henry. Good to see you again. Yeah, for the camera, like there are no specific specifications, I would say. For example, the camera that I used there was integrated within a Google Pixel 2 XL, which, as I may know, the current model of the Google Pixel is about 6. So you can tell how far ago that was, and we got pretty good accuracies from that. However, you can also use like a much better camera and get and still be able to get really good accuracies. You would get better models basically. But I would say, yeah, with any camera, once it's able to capture where the stress is, that's the most important detail. So any camera that's available in the market right now, I think would be very useful. The higher end cameras would obviously be better in terms of like a phone, like let's say the Samsung S21, for example. That would give you resolution, but the resolution we had on that, I think, was very limited, and we still got very results. I recently did another model using a high-end camera, and that was able to get better results, but I don't think it was sufficiently a huge amount better that that warranted the high specs. So I would say basically for a developing country, once you have the data and the number of images, that's more important than the having a high quality image. It's more about like to have a database that considers the different factors that are available within a data set, looks at the different road sections, and basically captures what exactly is going on in that network. I hope that's clear. But we can also have a further discussion on this directly. At any point, I'm available. And coming from a developing country as well, I'm also interested in developing stuff for them. So shoot me an email and we can discuss further. Philippe, you can go ahead.
Thank you for the question, Henry. Basically, my take on is that basically what I developed during my thesis was a framework that is a bit advanced, and its application to different, even developed countries, or is a bit, I would say, a bit tricky in the sense that you need certain data, you need to build a traffic model, and you will consider a lot of possible disruption scenarios. But still, I think the general idea is transferable to any kind of applications. You just have maybe to lower the complexity of the analysis and to focus on what you can in the data that you have. To give you an example, in the work that I do now, I did a consultancy for Ouagadougou in Burkina Faso, where we applied something similar, looking specifically at floods. So the idea was not to compute a lot of scenarios, but to understand the impact of flooding on the road network and to allow them to identify roads that should be prioritized for resilience investments. So I think that's something that I can follow back with you after that. Maybe we can have a talk to see possible collaborations as well, because I think that's something that we are looking into as well.
Thanks to everyone. David, I think the question time can be considered finished.
Thank you.
Any further question? Just, I don't think so. Okay, Dave, I think.
Thank you, Gaetano. Thank you, all the speakers, and thanks for all of you done for the project. Really, I'm really pleased to see that the fellows are now working on possibly sometime the same topic they developed during the PhD or being researcher. So what was the aim of the project? To actually create a generation of researcher that could implement the vision is actually happening, which is great. So really, thanks to all the fellows and to the supervisor that have guided them. So I will say now, again, Gaetano, thank you for managing this session, for sharing it.